At the heart of Japan, between the islands of Honshu and Shikoku, spans a colossal structure that alters the very landscape of the sky and sea. The Akashi Kaikyo Bridge towers above the waters, connecting two worlds with its graceful silhouette. It isn't just the incredible height or its breathtaking vistas that amaze, it is the intricate enigma of its main cables. Each one contains 36,830 individual high-strength steel wires. This astonishing arrangement begs the question, why are the world's longest suspension bridge cables made of thousands of wires, when one seemingly solid piece of steel could suffice? This question may lead us into deep waters, but as we dive deeper, we will uncover the precise interplay of strength, flexibility, and the uncanny resilience of engineering that prevents collapse. By the end of this journey, you will not only understand the reasoning behind this method but also appreciate the thoughtful complexity of the structures that adorn our world. To appreciate the need for such extraordinary design, we must first consider the physics involved in cable-stayed and suspension bridges. Imagine standing beneath the suspended cables as they carry massive loads, experiencing the tension in the air. The primary function of these cables, made of thousands of smaller wires, is to distribute weight. They endure enormous tensile forces, typically seen in structures bearing loads of several thousand tons, while also withstanding environmental conditions like wind and earthquakes. Take the Akashi Kaikyo Bridge itself. The main cables are each about 1.2 meters in diameter, and when you consider that they must support the weight of more than 200,000 tons of bridge, vehicles, and pedestrians, the challenge becomes clearer. A single, uniform steel cable of that size would be more prone to failure due to its inherent properties. When you think about it, a solid rod is similar to a delicate glass object, perfectly strong until it isn't. A single surface crack on a monolithic steel rod can lead to catastrophic failure, sending the cable crashing down. If that were to happen to the bridge, the results would be disastrous, not just for the structure but for safety on a critical transport route. But let's explore the mechanics at play in these bundles of wires. Each of the 36,830 wires in the Akashi Kaikyo's main cables is relatively small, roughly 5 mm in diameter. The beauty of having so many wires is their ability to accommodate localized failures. If one wire breaks, the load gets redirected to the neighboring wires, allowing the entire cable to maintain its structural integrity. This design minimizes the risk of collapse compared to a monolithic rod, which would suffer immediate failure upon the first fracture. Real-life examples illustrate this point. The Tacoma Narrows Bridge, nicknamed Galloping Gertie, is a cautionary tale of design flaws in bridge engineering. Opened in 1930, it spectacularly collapsed just 4 months later. The failure occurred partly due to the inadequate design of its cables, which could not adapt to the forces of wind. The Akashi Kaikyo Bridge, completed only after years of careful engineering, was designed precisely to understand and mitigate such risks, ensuring it would remain stable even in severe conditions. Furthermore, when designing structures like the Akashi Kaikyo, engineers must also consider dynamic forces such as vibrations and changes in load. The bridge features a sophisticated oscillation control system to handle dynamic responses created by wind and traffic. By using a bundle of wires rather than a single piece, the main cables can absorb these vibrations more effectively, leading to increased stability. Now, let's explore this a bit deeper. Have you ever wondered what happens in extreme weather? The Akashi Kaikyo Bridge, with its vast spanning distance of about 1,093 meters, must endure the powerful typhoons that often sweep through its region. If we were to imagine the main cables as a giant elastic band stretched across the horizon during harsh weather conditions, they must flex but not snap. A solid monolithic rod would have a very different response. It would not bend and instead be susceptible to breaking under immense wind pressure. Conversely, the flexibility provided by the bundling of wires allows the system to respond without losing strength. Now, before we continue, let's engage with a question. If you could stand beneath any bridge in the world, marveling at its design, which one would you choose? Perhaps you have a favorite structure, or maybe you think of one that inspired awe with its innovative engineering. Share your thoughts below. Returning to our exploration, let's address a misconception that many may have about these structures. It's a common belief that more is less, that a thicker cable made of fewer wires would offer greater strength. Here is where engineers often do the exact opposite. The design of using thousands of smaller wires reflects the accumulated wisdom found in centuries of engineering evolution. This intricate technique provides redundancy, a safety measure. Should any individual wire fail, others will bear the load. This concept was exemplified in the design of the Brooklyn Bridge, completed in 1883. Its main cables are constructed from more than 21,000 individual wires. Each wire contributes collaboratively to the strength of the whole system, ensuring that the bridge can endure, even when faced with localized vulnerabilities. As the Akashi Kaikyo Bridge stands as a testament to this principle, it also reflects an acknowledgement of the natural forces that can threaten even the most impressive man-made structures. Engineers often account for the potential of earthquakes, especially in a region as seismically active as Japan. The design anticipates motion, and because of their cable construction, the flexibility and load distribution capabilities become paramount to safety. This anticipation and adaptation are what make such massive projects feasible and sustainable. Now, let's take a moment to reflect on scale. The Akashi Kaikyo Bridge is not just an engineering marvel, it represents human ingenuity and an appreciation for the challenges imposed by nature. Those 36,830 wires are not merely components, they are symbols of our ability to confront the forces around us and create solutions. To conclude, we acknowledge that we live in a world where invisible engineering principles empower the visible structures we cherish. The complexities of cable construction in suspension bridges illustrate how careful design, awareness of failure modes, and flexibility can combine to create safe, magnificent structures. As we look around, we find ourselves surrounded by impossible machines that somehow just work. Subscribe, one giant decoded at a time. To deepen our understanding of how these cables function, it is essential to examine the properties of the individual wires that form the core of the suspension system. Each wire in the Akashi Kaikyo Bridge is crafted from a high-strength steel alloy. This choice of material significantly enhances the tensile strength of each wire, making it capable of withstanding the immense forces exerted upon it. In fact, individual wires can have a tensile strength of roughly 1,400 megapascals. By comparison, standard mild steel has a tensile strength of only about 400 megapascals. This marked improvement allows the resultant cable to better handle the variable load and stress it experiences over time. Moreover, these wires are subjected to techniques like cold drawing, a process that stretches and compresses the metal, enhancing its strength properties even further. A wire's strength is not merely added when composed of some of the most advanced steel alloys, it is transformed into a comprehensive system capable of absorbing and redistributing forces in ways a solid steel rod could never achieve. Some might wonder how such a multitude of wires can all work together effectively. This is where the concept of wire twisting comes into play. In the cables of the Akashi Kaikyo, each group of wires is twisted together in a helical pattern. This configuration reduces the likelihood of wear and tear among individual wires caused by friction. The twisting also allows for better load distribution throughout the cable, as it ensures that the load does not rest disproportionately on any single wire, which could otherwise lead to premature failure. One might visualize each wire as a strand in a woven tapestry. When tensions arise, if one strand begins to fray under stress or develops a flaw, the others within the weave can hold the fabric of the structure together. This weaving strategy is crucial not just for load distribution, but also for accommodating movement. As the winds shift or traffic vibrations travel through the bridge, the design allows for slight flexibilities, preventing catastrophic failure while ensuring the integrity of the suspension cables remains intact. Now, let's shift to a fascinating engineering anecdote that occurred in the early days of the Golden Gate Bridge, completed in 1937. The main cable is composed of 27,000 wires. In one winter, an unexpected snowstorm caused ice accumulation on that bridge, adding immense weight to the structure. At the time, thousands of impatient workers remained suspended high in the air, continuing work on the safety cables. As the snow started to melt, an extra layer of unpredictability arose, causing vibrations and oscillations. Fortunately, the extensive wire configuration allowed the cables to flex and subsequently adapt to the increased stress without any issues. The architects and builders designed it knowing that this dynamic flexibility was not just a feature, but a non-negotiable safety requirement. Another aspect worth exploring is the maintenance of these cables over time. The Akashi Kaikyo Bridge's long design life of roughly 100 years requires regular inspections and maintenance protocols to ensure the performance of each wire. Engineers must constantly monitor for any sign of corrosion or degradation, which is a natural enemy of steel structures, particularly those exposed to sea air and moisture. Therefore, reliable maintenance is necessary, and often, redundant systems are put in place to compensate for any individual wire that might show signs of wear. The structure itself is periodically sandblasted and painted, renewing its protective layer. During these maintenance phases, engineers can identify specific members, individual wires that might be showing premature fatigue, thus ensuring that the entire cable assembly continues to function effectively and safely. This reflective process reveals the importance not only of initial design but also of how we treat and maintain our engineering marvels over time. In the context of the Akashi Kaikyo Bridge, we also need to underline the role of technology in advancing our understanding of these complex systems. Engineers have deployed various forms of non-destructive testing, including ultrasonic inspection, magnetic particle testing, and dye-penetrant tests. These modern techniques allow for internal assessments of the steel wires without compromising their structural integrity, providing thorough checks on the health and safety of the main cables. Consider also the integration of digital sensors embedded in the cables, observing real-time structural effects. These sensors continuously collect data on stress and load, allowing engineers to monitor performance and make informed decisions about maintenance. A historic example can be found in the Mackinac Bridge, where sensors gather data to ensure the longevity of its suspension cables. Their findings augur not just for repairs but for overall better designs in the future of suspension engineering. An important note of advancement in bridge design is the predictive modeling software available to modern engineers. These platforms allow engineers to simulate different stresses and movements the cables would experience. This simulation facilitates understanding how materials respond under various load conditions, ultimately leading to an even more robust design. Engaging with how a bridge operates in the context of earthquakes can lead us back to the Akashi Kaikyo. Its design, completed after years of extensive research and testing, meticulously accounted for seismic activity. The region experiences, on average, several earthquakes each year. To address this, engineers integrated a variety of intelligent design aspects, including a flexible structure and a deep foundation that extends into the bedrock beneath. The motion experienced during seismic events, paired with inter-restraining devices, sees the bridge handle oscillations yet maintains its structural safety. Historically significant earthquakes also play a role in guiding modern engineering principles. The Great Hanshin earthquake, occurring in 1995, served as a wake-up call for the Akashi Kaikyo's design processes. Its devastating effects revealed vulnerabilities in many structures. The bridge was under construction at the time, and adjustments were made to its design integrating learnings that would emerge in its completion. Reflecting on these revelations, it becomes increasingly clear why the use of thousands of wires is not simply a design choice but an elaborate tapestry of engineering thought. The cables, in their effective juxtaposition of strength and flexibility, serve as the ultimate testament to human ingenuity in overcoming forces of nature. The incredible complexity involved in crafting these cables not only reflects various engineering principles but tells a story of resilience. As humanity continues to face challenges posed by ever-evolving environmental conditions, the designs of bridges like the Akashi Kaikyo provide vital lessons in adaptability and foresight. To traverse the skies above our roads and cities, cables made from thousands of individual wires underscore our ability to innovate solutions to complex problems. These massive machines, while often taken for granted, serve as remarkable epics of engineering prowess. As you look around, consider the invisible frameworks that sustain such visions of architectural splendor. As we conclude our exploration of suspension bridge cables and their intricate qualities, we stand in awe of the profound wisdom of engineers who have crafted their design based on nature's unyielding principles. We are surrounded by impossible machines that somehow just work.